In this demo, we will look into compression when getting data. We're looking at the compression samples class. Let's take care of the plumbing. We're kinda used to that by now. So, we start by injecting an HTTP client factory and our options wrapper. And then let's add a new method. Let's name it getPosterWithGzipCompressionAsync. In it, we create a new HTTP client and we ensure that we call it from our runAsync method. We await that call, and to be able to do that, we need to mark the runAsync method with the async modifier. Alright, that takes care of the plumbing. I named the method getPosterWithGzipCompressionAsync. Gzip is one of the compression formats supported by our API. Another common format is Deflate. If you're integrating with an API, check the documentation to see which forms of compression are supported. Let's create a new HTTP request message. Through this we can get one poster, and we set the accept header to application.json. We know from previous demos that we can use this accept header to ask for a specific format. A likewise header, accept encoding, can be used to ask for a specific encoding if the API supports it. That's what we're going to use now. We only want to accept responses that are compressed with the gzip format. To do that, we add a new value to the accept encoding header, gzip. That should be sufficient to ensure that we get back a compressed poster. For sending and reading out a response, we use the best practices we've learned about up until now. That means that we send the request by passing through response headers read as HTTP completion option, and we use a stream to read out a response. To deserialize, we use system.text.json, so I need to import the system.text.json namespace for this to resolve, and I also need to import the movies.client.models namespace for the poster class to resolve. Alright, let's put a breakpoint right before we deserialize, and let's make sure we call this method when we start up the application. So we navigate to the program class and we ensure that the compression samples class is registered on our container. And let's give this a try. We hit our breakpoint. So far, so good. Let's continue. And we hit an exception. Apparently, we can't just deserialize this. An unexpected character was encountered. Well, to be honest, this isn't that unexpected. We are now dealing with a compressed response. So far so good. That means that our accept encoding header had the effect we wanted. But we still have to decode the response. And that's what we forgot to do. We can do that with an HTTP client handler. And in fact, we even know how to do that already. In the module on working with HTTP client factory, we learned how to configure the primary handler. That is what we need to do here as well. Let's open the program class. We configure the primary HTTP message handler by newing it up. That code is already there. And on that new instance, we set automatic decompression to gzip. There we go. Let's give this another try. We again hit our breakpoint. Let's continue. And this time, deserialization did work. We've just improved performance with compression thanks to much lower bandwidth use. Note that the code we wrote in the previous demos, which all use this Movies API client, still works as well. The handler will only try to decompress when the content is actually compressed. It knows this by looking at the content encoding header of the response. Up next, sending compressed data. In this demo, we will learn how to work with compression when sending data. Let's start by adding a new method for that. Send and receive poster with gzip compression async. We'll also ensure that this method is called when we run the application. As far as the content of this method is concerned, I'm gonna start by copying over the content from the post and read poster with streams async method we created in a previous demo. This ensures that we're already working with the best practice approach for sending and reading data. So let me copy this. And there we go. Now let's modify this method so we work with compression. There's two things we need to do for that. First, we want to state that we will accept gzip encoded content. Like that, the response will be compressed. We know how to do that from the previous demo. We add an accept encoding header value, gzip. Then we need to compress the payload. And that payload, that is our poster for creation. We're currently streaming that to the memory content stream. So currently, the memory content stream is passed when sending a request. We want to change that so a compressed content stream is passed. To compress, additional streams exist in .NET, like gzip stream and deflate stream, depending on the compression algorithm you want to use. The first thing we want to do is create a new stream which will hold the compressed content. We'll name that compressed memory content stream. We're still working with streams, and as we know, those need to be disposed of, so we surround this with a using statement. Inside of that, we use the gzip stream class. The idea is that we will use it to compress the incoming memory content stream. We pass through the destination. That is our compressed memory content stream, and we also pass through compression mode.compress as we want to compress. In case you ever need it, you can also use this class to decompress, as you could probably guess. Then we want to copy over our memory content stream, which contains the uncompressed data, to the gzip stream and flush it. The result of that is that the compressed memory content stream will contain the compressed data coming from the memory content stream. We also set the position back to 0, as it's this stream we will now use to stream data when posting, and we want that to start from the beginning. And that is indeed the last part of the streams puzzle. Instead of passing through the memory content stream when newing up a stream content object, we pass through our compressed memory content stream. And that takes care of compressing the response body together with using streams. The one thing we still need to do is ensure that we let our API know that the request body content is encoded and how it's encoded. So to that avail, we add a content encoding header with value gzip. This should be it. Let's set a breakpoint here right after we deserialized the poster we just created and got back, and let's give this a try. We hit our breakpoint, and here's our poster. We are now using compression both on sending and receiving data. Let's continue with the module summary. When you enable compression, the data that is sent over the wire is smaller, which results in less bandwidth consumption and thus often faster performance. If an API supports compression, it is sufficient to set the accept encoding header to the compression format we want to accept and to enable automatic decompression. To compress a request body, we can use compression algorithm specific stream classes like gzip stream or deflate stream. In such a case, we need to let the API know the compression format of the request body via the content encoding header. Imagine sending a request from an application page to download a large file. The user might get tired of waiting and might navigate away. In that case, and in other cases, we want to cancel that request. In the next module, we will learn why and how. It's often overlooked, but cancelling requests can be beneficial to performance, both at level of bandwidth consumption and scalability. Let's learn how. I'm Kevin and I'll guide you through this. We will start by learning why we should cancel requests when we no longer need them, say when loading a large movie trailer. While doing so, we will learn about the cancellation token source and the cancellation token. We will learn how to cancel a request, and we will learn how to handle a cancelled request. Let's dive in. Imagine we're using HTTP client to get a movie trailer. Chances are that the user of your application will navigate away or press a cancel download button. In such a case, you want to be able to handle that instead of just letting the request continue. The reasoning behind this is that behind the scenes HTTP client works with async tasks. If you're interested, I've got a full course on using async when building an API with ASP.NET Core that goes into a lot of detail on those tasks and asynchronicity. For our purposes, in this course, it's important to know that cancelling a task that's no longer needed will free up the thread that is used to run the task. That means that that thread is potentially returned to the thread pool where it can be used for other work. So that is one use case we have to cover. In this case, we are cancelling the task. Or rather, we are requesting HTTP client to cancel the task. There's another reason though. It's not unheard of for a timeout to happen. If that happens, we want to be notified of that so we can gracefully handle such a timeout. In such a case, it is due to the timeout that the task gets cancelled. But we still need to be able to gracefully handle that cancellation. Both cases are true for all types of resources. Even when getting one movie, a user might navigate away or experience a timeout. Let's learn how we can support that next.